Okay, learners, in today's lesson, we're going to be looking at Theorem 8, and it states that if two tangents are drawn from the same point outside a circle, then they are equal in length. So for this theorem, let's just quickly look at the proof. Then for the proof, you'll only be given, so in your diagram, you'll only be given this tangent AB, and tangent AC, right? Then you will have to construct the broken lines here. So you'll construct radius OB and then also construct radius OC. So as we can see here, we'll say join OB, OC, and also we'll construct a line from the center here to the point where the tangents meet, right? So this will be OA. Then having to construct this, you can now say here it's B1 and there it's C1. Then now we can see that we have two triangles here, which is triangle OBA. So this is a triangle OBA, and then down here we also have another triangle OCA. So if you can just follow there, we have another triangle OCA. Then now we're just gonna prove the congruency between these two triangles. So we'll say OB is equals to OC. So we can see OB is equals to OC because they are radii. Remember, OB is a radius and OC is a radius, and then collectively we call them radii, right? And then also again we can see that the B1 and the C1 that we constructed there, they give us 90 degrees. Why? Because this is tangent perpendicular to radius. So remember, tangent perpendicular to radius is equals to 90 degrees. So 90 tan perpendicular to red. But also again, we can see that OA here is a common side. So OA is in triangle OBA and also in triangle OCA. So we have OA being the common side. Now, since we have proven with two sides and an angle, we can say that these two triangles are congruent. So we'll say triangle OBA is congruent to triangle OCA, and the case is right angle hypotenuse side, right? So we proved with a right angle, we proved with a hypotenuse side, which is the OA, and then we proved with yet another side, which is OB and OC, which in this case are the radius. Then if we have proven that, we can then conclude that if these two triangles are congruent, remember congruent means that everything is the same here. The angles and the sides are equal in length, right? So that means we can now conclude that AB is equals to AC, which proves our theorem that says that tangents from the same point are equal in length. So these tangents are coming from the same point A, and they'll be equal in length. So AC here, the point from A to C and the point from A to B will be equal in length, right? So without any further ado, now let's look at the activities that we have for this theorem. A. So in this activity, we are required to find the values, the missing values A, B, and C, right? So, but then in order to calculate A, let's check. We can see that AP will be equals to PT. What's the reason for that? So we say AP is equals to PT because these are tangents from the same point. So we can see AP is a tangent to the circle and PT is a tangent to the circle. So we say tangents from same point. Then if we have tangents from the same point, they are equal, right? That means we have formed an isosceles triangle here. So if you can look at triangle APT, we can see that this is an isosceles triangle, meaning if this is A, this is also A. So now in order to calculate A, we can just say A plus 50 degrees is equals to 180 degrees. And the reason is sum of interior angles of triangle. Now A plus A, that's 2A, and then transpose the 50 to 180 minus 50, and then that's 2A is equals to 130 degrees, and then divide both sides by 2. So our A is going to be equals to 65 degrees, right? Then we have the size of A. Then to calculate the size of B, can just check here. We have OA. OA is the radius and OT is the radius. So OA and OT are radii and they're equal. They form an isosceles triangle. But what else do we see? We can see that this is a radius meeting with a tangent. Where a radius meets with the tangent, we have what? 90 degrees. But then remember here we already have this 65 degrees. So what's the angle that we should have here? So we can say A2 should be equals to 90 degrees minus 65 degrees, and we say the reason is tan perpendicular to radius. So our A2 is going to be 25 degrees. But then remember A2 here, if this we say this is an isosceles triangle, AOT is an isosceles, that means A2, so we'll say but A2 is equals to T2, and then they're both equals to 25 degrees, right? Then we say the reason here is base angles of isosceles. Now we have 25, that's right, we have 25 here and 25 here. So we can use the sum of interior angles of a triangle to look for the value of B. So to find B, we'll say B is equals to 180 degrees minus 25 minus 25. What's the reason for that? Sum of interior angles. Sum of interior angles of triangle. Then calculating B will give us 130 degrees. Now to find C, we can see that AT here is a chord subtending an angle at the center B, and AT is a chord subtending another angle at the circumference. So we can see our theorem here, angle at the center is 2 times the angle at the circumference. So meaning our C is equals to 65 degrees. Because remember, the angle at the center has to be half the one that is the angle at the circumference, meant to say has to be half the angle at the center. So 65 degrees, and then we say angle at center, because from the theorem that says angle at center is twice the angle at circumference. So let's move to B. In B, we are required to find the missing values X, Y, and Z. But then from here, we can see that BE is equals to DE. That one is given, right? So we are given that BE is equals to DE. Therefore, we know that this is an isosceles triangle. What do we know about the base angles of an isosceles triangle? They are equal to, that means X is equals to 30 degrees. And the reason we say base angles of isosceles. Or you can indicate that BE is equals to DE. Right, then if we have 30 degrees here, how are we going to find Y? We can use the sum of interior angles of a triangle. Then we'll say Y is equals to 180 degrees minus 30 degrees minus 30 degrees. Then the reason is sum of interior angles of triangle. Then what will be our Y? Y is going to be 120 degrees. So we have this 120 degrees here. Then to look for Z, remember you cannot say this is angle at center twice the angle at the circumference, because we can see that Z here is outside and Y here is at the circumference, not at the center. Then how are we going to find Y? Let's use our theorem number 8 now, that says tangents drawn from the same point will be equal. So we can see that the tangents DC and BC are drawn from the same point C. So that means BC is equals to DC. So we can say BC is equals to DC. Why? Because tangents from same point. Tangents from same point. So if BC is equals to DC, what do we know? That means this angle here will be equal to the whole of this angle. But then what do we have here? We already have 30 degrees here, and then with this 30 degrees, that will give us 60 degrees here. So if we have 60 degrees, and then we also have 60 degrees there, what will be the angle here? So we'll say, let's start off by saying angle angle DBC is equals to angle BDC. And then we say these are base angles of isosceles. Base angles of isosceles, right? And then we know that they are equal to 60, right? So that's 60 degrees. Then to find Z, let's use the sum of interior angles. So Z is equals to 180 degrees minus the 60 degrees from here, and then minus the 60 degree from there. So minus 60, and then our reason is sum of interior angles of triangle. Then our Z will be equals to 180 minus 60 minus 60. That's equals to 60 degrees. Awesome.